I'm going to record the whole thing so that if we need to, if somebody has missed it, it doesn't matter. Okay, let's look at the next bit of the question. The next bit was about homologous series. You have to know 3 things about homologous series. Homologous series, and this ethyne is an alkyne. Examples of homologous series. Are the alkanes, alkenes, alkynes, alkanols, alkanoic acids, and esters. Now, all of these you have to know about, every one of these. And today we're looking a little bit at these 2, really simple, start simple, just with these ones. The last question, question 1, was about alkynes. That was about spotting that. But every one of these is a homologous series. And you have to know something about homologous series. 3 things. Can anybody tell me something about homologous series? 3 things about homologous series. Somebody tell me 1 thing about homologous series. What do they have? Somebody switch on a microphone and tell me, or write it down and show me something about homologous series. They have some things in common and some things very different. Anybody? Excuse me. No? I'm sure you know this. Oh, somebody's writing at the back. I'm going to write them because it's important that we get on and we do quite a lot of chemistry. So, the things that they have in common. 1 is the same general formula. It is the same general formula. Okay, each one. Were you going to show me? Guy with a pink hat. Were you going to show me? Were you going to show me the things? I can't read it very easily. Can you put it a little bit closer? Yeah, it is a bit small. Don't worry, it's okay. Very similar chemical.
Mark,
Yes?
Genesis is asking you let them in.
Oh, sorry, I haven't seen them. Apologies. Are they in now? Yes. So they have very, very similar chemical properties. Is this too small for you to see? Do you want it bigger? Hi again. Hi, Michael. You want it bigger? I'll make it bigger. So the general formula, they have the same general formula. So for instance, the alkanes, I'm sure you know this, CnH2n plus 2. You have probably done this, or 2x, it doesn't matter. Do you use N or X? N? Is N okay? Have you used this before? Yes, okay. Oh, not so good, okay. Genesis, have you seen this before? Okay, good. All right. So they have the same general formula. They have very similar chemical properties. This means they react the same. In a chemical reaction, there always is a change from one molecule to another one. It is always different afterwards. They have, the third thing they have is a trend in physical properties. A trend. In other words, they start with one physical property and it changes across the series. Physical properties is all about things like melting point, boiling point, how easily they evaporate, viscosity. These are words which we will come across. But anyway, that's it, a trend in physical properties. So for instance, if we look at a trend in physical properties, we might choose boiling point. And as the number of carbons increases, the boiling point increases. Okay, I'll draw a graph in just a minute. The general formula you have to remember for each one. The chemical properties, we're going to look at one in just a minute, chemical properties. They have to have the same sort of chemical properties. Now, you may have learned that this is because they have the same functional group. The functional group we will deal with in just a minute. So these are the three main things that you have to say about homologous series, like question 3 from the paper. Okay? Something on the chat. Okay. All right, so we're going to look at another question and we're going to see whether it makes sense. So here we are. This is we're going to move on a bit. So in this one here, we worked out how to do this. The general formula of the hydrocarbons, we haven't done, we will just do that. And the structural formula of the fourth number of the series, we will just do that. So going back to that question, so this is the answer to question 2 and 3. What is the general formula for this group of alkynes? What do we write here? If we have a certain number of carbons, what is the number of hydrogens? Have a quick moment and think about that. Have a think. Has somebody got an answer? Tumaini. Somebody wants to tell me the answer. The guy to the left of the man with the pink hat. Genesis, have you got an idea of what this would be, what I have to do here? No? Okay, all right. Let's see if Tumaini can do it. Tumaini? Up a little bit higher. Very good. Not, hang on, wait a minute. Just show me once more. I think you said +2. Can you show me again? Well, no. If it was this, then see what happens. If I make n 3, then this will be 2 times 3 and 2. This would be 6 plus 2, which is 8. We need it to be 4. This is okay for alkanes. We need this to be a different number. I'll show you. If I double this 2n and go minus 2, then it makes sense. Because if I go 3, so this number here will be 2 times 3, take away 2, 6 minus 2, 4. Okay? So the homologous series, the general formulas I will show you. So the alkynes is this. Okay, alkynes, it's this. It's quite a nice, simple sequence. I will show you. Is everybody okay on this? Genesis, do you understand this? Okay, good. So, that is alkynes, alkene, alkane, alkane, CnH2n plus 2. So we double the number of carbons and add 2. Alkene, CnH2n. Okay? So you need to remember this bit. So for an alkane, we double the number of carbons and add 2. Alkene, just double. Alkyne, double, take away 2. That's how we do it. And then it asked for the structural formula of the fourth member of the series. The fourth member will be C4. C4, it's an alkyne, so it will be 2 times 4 minus 2. So it will be C4H8 minus 2, 6. Now, this looks like the answer, and they accept this as the answer, but it's not right. Because actually, the fourth member of the series has got 5 carbons. I will say why in a minute. So C5H, 2 times 5, minus 2, is C5H, 10 minus 2, 8. So why do I say that the fourth member is not C4? Why is it not C4? It's C5. Why is the fourth member C5? Has anybody got any idea? I'll tell you. All alkynes have this. Every alkyne has this. If you have C triple bond C, then the first member of the alkynes must have 2 carbons. So the first member is C2H2. That's the first member. The second member, C3H, 2 times 3, 6, minus 2, 4. So the first member, second member, third member, C4H6, fourth member, C5H8. This one. So you have to be careful because with alkanes, the first member is methane. But for alkenes and alkynes, there is no 1 carbon member of the series. They all have 2 carbons. Okay, so because you have to have, if you have double bond in alkenes, triple bond in alkynes, you have to have 2 carbons to start with. Okay, they have to attach. So for alkanes, methane, ethane, propane, butane, pentane. For alkenes, first member, ethene, not methane. Ethene, propene, butene, pentene, and so on, okay? So it asks for 4th member of the series, 4th member, first member, C2, and so 4th member, this one. Now, this is a molecular formula. So molecular formula. Structure. Sometimes they just call it structure formula. In KCSE, they quite often call it structure formula. It's not quite right, but it's okay. This means drawn out. So I take 5 carbons, 1, 2, 3, 4, 5. It doesn't matter where I put the triple bond. So I could put it here. I could put it here. So this one then would be single bond, single bond, single bond. And then all I do is I put all the hydrogens on. Each carbon, 4 bonds. This carbon, 1, 2, 3, 4. 1 hydrogen here. This carbon, 1, 2, 3, 4. No hydrogens. This one here, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so this is one isomer. Isomer. The isomers have the same molecular formula, different structural formula. So this one here is going to be different because it's going to be like this. This carbon, 1, 2, 3, 4 bonds. This carbon here, 1, 2, 3, 4, no hydrogens. This one, 1, 2, 3, 4, no hydrogens. This one, 1, 2, 3, 4. This one, 3. So these two are both correct, both correct. And there would be, if I move this to there, that is another isomer. So isomers, same molecular formula, different structural formula, okay? Now, we said that they have the same general formula, CN, in this case, 2N minus 2, alkanes, CN, H2N plus 2, you have to learn those. If in an examination, if you look at it, you write out the formula, make sure it fits. Like when somebody from Tumaini suggested that it was 2N plus 2, work it out, make sure it fits. Don't just go, hey, that'll do. Okay, let's go back to the questions because I want to move on to something slightly different. Okay, so here are the questions again. And I'd like you to try to do the questions yourselves at some point. So we have done this, that's okay. Now let's look down here, because this, I'll make it a bit bigger. Excuse me. This is about the trend in physical properties. This is what homologous series are all about. Same general formula, same chemical properties, trend in boiling points. And I'll just do that on the board in just a minute. And then it says, explain why, and this is a chemical property, why enthalpy of combustion is negative. And then it says, state the products of complete combustion. So we'll look at that, okay? So the first one is boiling point. And it goes like this. So any homologous series, same general formula. Now the boiling point, if we go up the side and we go for number of carbons along the bottom, 1, 2, and so on, then the graph looks like this. Okay, the graph looks straight up here. But this isn't 0. This is a negative number. So methane, let's say we are talking about alkanes. Methane, first one, this number is minus 169 degrees Celsius. That's really cold. So in other words, don't put 0 here. Don't, if you're asked to draw a graph, do this. If you're asked to describe it, then in the question, you go as the number of carbons increase, so does the boiling point. Okay, that's what we would normally write. They have given you, in that question, they've given you many lines. Not necessary. If you just say, as the number of carbons increase, the boiling point increases, that's enough to explain that trend, okay? As the number of carbons increase, the boiling point increases. There are differences. So for instance, if you have a chain like this, and then you have it branched instead, the branched ones have lower boiling point, but don't worry about that too much. If they ask you to explain this, then it is because of the intermolecular forces. Have you come across intermolecular forces? Genesis, intermolecular forces? Good. Tumaini? Intermolecular forces? Okay, good. So, as the number of carbons increase, boiling point increases. I'm just going to get rid of this. This is because the longer chains have more powerful, you could call them strong. Strong is okay, powerful. Intermolecular forces. Now, the intermolecular forces, you have to say what they do. Intermolecular forces holding the molecules together. Now, if the intermolecular forces are holding it together more, we need more heat to pull them apart. Okay, we need to put more heat in to pull them apart. Now I'm gonna show you a little bit of chemistry. I'm gonna show you just a little bit because I've taken nearly an hour and we haven't done a lot. But if you've got a chance to look at the questions, what I will do is I will send to the supervisors all of the answers, okay? I will send them all the answers, then you could have a look at the questions, the rest of these questions, and then you could go through them, okay? You all right, yes? Good. Okay.
I'm really good.
You're really good. That's good. That's good. Yeslin's really good. Everything's okay.
Good lesson. Keep it going.
I'm keeping going. I'm keeping going. So I'm going to go back to the questions now. I'm just going to ask you which ones were most difficult so we can look at them later. So I'm going back to the questions now. Here are the questions. I will do this one, why the combustion is negative. I will do this one because I'm going to do a small experiment. I'm going to ask you about number 5. This is catalytic cracking. So I'm going to ask you, catalytic cracking, is that okay or not? Thermal decomposition, catalyst, and so on, okay? The next question is about naming. Are you okay on naming these chemicals, okay? Because naming is very important. You should know, you should see this and go, ah, that is alkanoic acid, 3 carbons, propanoic acid. So I'm going to ask you about those. So the first question, the first one of those questions was about catalytic cracking. And I need you to show me thumbs so I know whether to do that one or not. Is catalytic cracking, is thermal decomposition, is this okay or not okay? Genesis, thermal decomposition, catalytic cracking, or is that okay? You know this? Genesis? No, okay. Tumaini, oh, okay, you don't know it either. Okay, that's okay, we will do it. We will do it. And the last question was about naming. Can you do naming okay? Genesis? Genesis, is naming okay or not okay? Naming is good. Okay, Tumaini, okay or not okay? Naming chemicals. Okay, some good. All right, okay. We will do the catalytic cracking quickly and then I will show you a little experiment, okay? So let's just have a look at the catalytic cracking one. Here it is. Okay, let's make it a little bit bigger, get rid of that. Okay, whoops, hello. Okay, catalytic cracking is carried out by oil companies to produce high-grade petrol. And it says it's a type of thermal decomposition. What is thermal decomposition? What is a catalyst? And here's a cracking reaction. So I'm going to just write that down. Hang on. C10H22. Good. Okay, so I'm coming back. Okay, hi Genesis, hi Tumaini. Literally 10 minutes more and I will show you a little experiment and then we finish. Okay, so here we go. Cracking is really important. When we take oil out of the ground, we get a lot of different molecules. Some are short. Short molecules are very useful. So short means carbons with 1, 2, 3, 4, 5, 6, 7, 8, that sort of number, okay? Small number of carbons. That is because they burn easily and we use them as fuel. Fuel to cook, fuel to run the car, to run the truck, whatever, okay? Run the bus, okay. If the chain is too long, too many carbons, we have to cut it into small. When we do that, something funny happens. So I'm going to just show you here. It is what we call thermal decomposition. So this is the example C10H22. And they tell you that when it reacts, it does this. So C10H22 turns into C8H18. Now, in the question I gave you, it tells you what the other chemical is, but quite often it doesn't. So we're going to do it slightly differently. So I know that it is going to be some other molecule is missing. all I have to do is to balance the equation. So in terms of, if I write down what I've got on this side of the equation, I think if you're balancing an equation, quite often if you put the elements here and how many you have on this side, that side, it makes it easy. So carbons on this side, 10. Hydrogens on this side, 22. On this side, I only have 8 so far. I'm not counting those. And 18 here. So I know I am missing 2 from here. So I need 2. And I know 22 minus 18, I need 4. So here must be 2 and 4. To balance the equation, I have to have the same number of carbons and hydrogens both sides. So even if I did not know what this chemical was, this tells me the equation is not balanced. Because it's not balanced, I know I am missing 2 here, 4 here. So what I have here must be 2 carbons, C2H4, like that. So that is what it is. That's what the chemical is. If I draw these out, if I show the structural formula of them, this one here, if I look at it, I could start to draw it out and it will be 1, 2, 3, 4, 5, 6, 7, 8, and they are all single bonded, and there are hydrogens on every one of these positions. I'm not going to draw all the hydrogens. You can see what there would be there. This one is different. This one is this. So when we crack a long molecule, we always get a shorter one and an alkene. This is an alkane, and this is an alkene. We always get that. When we crack them, we always get that. That's really useful because I know in Kenya you ban plastic bags. Very good, well done. We follow you, it's very good. But this can make plastic. So I get from a not very useful molecule, I get a shorter molecule. This is petrol, that's good, and alkene, which will allow me to make plastics. Now, maybe we all want to reduce plastics, but at the moment we still use them, okay? And there are some things they are very good for, but we just don't want to throw them away. That's the first one, okay? That's what cracking is. It is called thermal decomposition. Thermal simply means something to do with heat. Decomposition means breaking down. So thermal decomposition means breaking something down using heat. And what we do is we heat this, it's around about 600 degrees Celsius, and we have a catalyst. And the catalyst is, there are many different catalysts, but one is aluminium oxide. And the aluminium oxide, a catalyst, speeds up a reaction. It speeds it up, but it is not changed itself. Right. I'm now running out of time, so I'm going to show you a little bit of an experiment. I'm just going to turn on the other camera. I hope that it's been useful. I have asked, for instance, Teacher Collins at Tumaini to tell me what topics he would like me to do, and I can do any, and I can demonstrate them without any trouble. But I thought just now I would show you some little experiments to explain some of the things we are doing. So here we go. I just need to change my camera. I hope you will still be able to hear me. So first of all, here is an alkane burning. Okay, this is methane. This is methane burning, and it's burning with a yellow flame. It's burning with a yellow flame because I haven't got oxygen moving into the bottom of here. Okay, this is what we call a luminous flame. But if we take an alkane and we add oxygen and we mix it with oxygen to start with, what we get is what we call non-luminous flame. Okay? Now that's quite important, because if we just saw it burning like this, we would think, oh, that's a luminous flame. Luminous meaning it gives out light. And that looks like something else. So what I want you to remember is it only counts if it is mixed with oxygen. Okay, so now I have two chemicals, two liquids. There is I'll get a little bit closer. Let's get a little bit closer, right. Here I have liquid A, and I'm going to take a little bit of liquid A, and I'm going to just put it on here. And I'm going to set fire to it. I'm going to try to set fire to it. Now that burns with quite a yellow flame. That is quite a yellow flame. It's not very smoky, but it is quite a yellow flame. Okay? Now I'm going to take another chemical. This is chemical B. And what I want you to do is to see if you can see any difference between the way they burn. Because sometimes they ask you something about a chemical and they say, ah. Now I don't know if you can see that. But this is a yellower flame. And there's quite a lot of smoke coming off this. This is yellower because this one is an alkyne. So the yellower the flame, the more carbons in it, the greater percentage of, oh, sorry, somebody's just trying to come in. The percentage of carbons. So if we take something, I'll do the first one again. If there are not quite so many carbons, it is less yellow flame. This is a yellow flame, but it's not got a lot of smoke, okay? When we look for something which burns properly, I will show you something now which burns really quite properly. I'm going to go over to another part of the laboratory, and I hope you can hear me. What I'm going to do is I'm going to put a liquid, and it's an alkanol. I'm going to put the alkanol, I'm going to get it to vaporize, to turn into a gas, then I'm going to set light to it, okay? And hopefully you will see something quite good. So I'm just going to turn this Bunsen off. I'm going to turn the camera around. So hopefully you will be able to see. I'll just get a bit closer, hang on. So it's going to be this bottle here. I'll come away a little bit. I think you like this one, Yestin.
I'm watching.
Yeah, good. I'm glad you're watching. Yeah, we can mostly see that. Okay, I'm going to turn the lights down because it will be more interesting. What I have here is an alkanol, propan-2-ol, and I'm just going to take a small amount of this. I'm just taking about 40 cubic centimeters, 40 mils. This is a water container. And hang on, just a moment. Now you know it's proper chemistry. So I put my 40 mils of alcohol into here, and because it's quite warm in the laboratory, the liquid is starting to evaporate, and I'm now going to help it evaporate by swirling it around the inside. Okay, so I'm coating the inside of this, hoping to make it vaporize more. I'm now just going to turn the lights out, and hopefully you can still see it at the moment. And what I'm going to do hope you can still see me. Is I'm just turning the excess liquid out. I'll move that out of the way. And what I'm going to do now is I'm going to light it. But I'm going to be a little bit careful. So I'm lighting it from a distance. Watch. Okay. So this goes really fast. This is like a rocket. What is interesting about this is I poured all the liquid out. Okay? So that in here now, if there's any liquid, it wasn't there to start with. And what happens is that as I turn it upside down, liquid comes out. That liquid was not there to start with. That liquid, I'm not going to drink it because it's got other things in it. But that liquid is water. Because one of the products of burning, of combustion, of alkanes, alkynes, alkenes, alkanols, alkanoic acids, is water. So I'll just come back to the other camera. Did you see it, Justin?
I did. Very impressive.
It's all right now.
Yeah, proper juju.
It is proper juju. Yes. So that is happening because when you write an equation for any organic reaction, any organic compound burning, so that was propan 2-ol burning, which is C here, 3H, 1, 2, 3, 4, 5, 6, 7, OH. I add oxygen, and it always produces just two things, CO2 and H2O. 3 carbons, 3 carbons. 7, 8, 4 waters. Total oxygens on this side, 6 and 4 is 10 oxygens. There is 1 here, so here I need 9, which would be 4.5. So I double everything, 2, 9, 6, 8. Okay, we're out of time. I'm sorry if I've taken too much of your time, but hopefully it was useful. And your teachers will be able to tell me what topics you would like to do, and we can do it another time. And what I will try to do is to do it after the end of your school rather than interrupting your school. But it's extremely nice to see you, Genesis. Thank you very much for coming. And if Tumaini is still there somewhere, it was very nice seeing them too. Okay, so I'm going to say bye-bye now. And thank you very much for coming along. Okay?
Thank you, thank you, thank you.
Cheers now. Bye now.
Thank you for a great lesson.
It's a pleasure. It's a pleasure, mate.
Thank you, Teacher Mark.
Yeah.
Thank you, Teacher Yestin. Organizer
Michael, are you all right with the team? You
Okay.
good? Yeah, okay.
If you can give Michael, if you could give Sophia some feedback so we know how to do it. Your students are very nice and they're very silent so
Yes,
far.
we
So
need to see more action. Yeah.
we'll warm them up. But thank you very
From
much
the
indeed.
students.
Thank you, teachers.
Yeah.
Thank you.
Mark, thank you.
Cheers, mate.
Asante sana.
Asante sana.
Ades, asante.
Kwaheri.
Kwaheri.
All right, Yestin?
Yeah, all good. Thank you.
All right.
Yes.
Have you got a class waiting at the door there?
Nearly. No, 10 minutes.
Yes.
It's all right.
Okay. Well done.
Thank you, thank you. That has gone well.
I think as well, actually seeing a chemistry lab brings it all to life a little bit as well.
It does, doesn't it?
Yeah.
Because not many of them will have been in anything like this.
No.
It's a shame, isn't it?
Yes.
Yes.
You know, you had this idea of using some of the labs in some of the, I think you mentioned a school somewhere.
No,
Braeburn.
Braeburn. No,
Braeburn.
what we were doing was talking about microscopes. I've forgotten that conversation, Sophia.
Yeah. Yeah, we needed to get a few microscopes.
Yeah, Braeburn haven't come back to me, so I think Braeburn, well, they haven't offered any microscopes, so.
Yeah.
If you, I mean, can you buy at least 4?
At least one per school.
At least one per school, so Billion's got one.
I tell you what, we have these things, these little cameras, okay? And these are about, now on eBay, they're about 20 UK pounds. And now that sounds like quite a lot, but with these, what you can do is you can get the microscope and it will produce a video of what the microscope is.
Okay.
Okay, so it's just a little, like, crappy little camera. Now, you have to make sure that they work with microscopes because some of them, because you have to be able to focus. This thing can focus here, okay? And we use that because if a teacher is trying to show something, it'd be lovely for everybody to have a microscope, but actually they can't, you know. Well, they do here, but, you know. So with this, you can then put it and you can show how you're focusing and how it goes in and out of focus and what to see. And then you can get somebody else drawing it on the board or whatever. It works really well.
Ah, excellent.
I'll find out. We've just changed to these big things that we use. I'll see if the school has any of these. Because if we had, I'll ask whether we have any spare ones, because it'd be dead easy to put them in a package and send them, and that way you wouldn't have to bother. But if you could get one microscope per school, and show them the wonders of, like, under a microscope, you know, just get something out of a puddle and look at it.
Yes.
Next, you could show us how it works with the supervisors one of the days.
Yeah, sure. No, not a problem. Easy.
Kirsten is a bit shocked.
No, I'm just realizing my fringe is getting longer and long. I'm in lockdown hair.
Ah, yeah, we're all in lockdown hair.
I think I've got lockdown moustache, lockdown hair.
You can do something with the moustache, mate.
Lockdown clothes.
do you know? Yeah. Do you know my daughter once, when she was about 5, she came out of her bedroom and she had no fringe at all, and I went, "What the?" And apparently she decided to straighten up her fringe, right? So she started cutting, and it wasn't quite straight, so she cut again and again and again and again until she had no fringe at all. And she went to school. I went, "Oh my God, okay, I'll pretend it doesn't matter." Anyway, she went to school and we had a phone call from the head teacher saying, "What have you been doing to your daughter?"
Oh.
No, you know. That was Rebecca, who was born at Glangwili, Yasin.
Okay.
It would have been nice to take a photo of that, so
Oh,
you
no.
can tease her later.
Oh no,
Tease her.
that'd be just so wrong.
So does she think of
Cruel,
herself does she think of herself as full-on Welsh?
She supports Wales in rugby. She loves Wales. You know, she quite often goes back. She married a Welshman.
Okay.
Her son is called Griff.
Ah.
You know.
Okay.
Yeah. So yeah, she's really misguided. Right, I better go because I've got a lesson just coming in a minute.
Thank you.
But thank you for organising it, Sophia, because I do enjoy it. But it might. I will try to find a time when I can consistently give the same time. It may be a Wednesday, but it would be better if it was at your time, 4 o'clock, wouldn't it?
Yeah, yeah.
Okay, I'll try and work it out. I'll talk to Yestin. We'll get something more worked out. Okay.
So what day
Sunday.
are you thinking of?
Don't know yet.
What is your day off? What is your spare day?
Well, the trouble is, if that 1 week it's Wednesday, the next week it's Thursday.
Yeah.
Okay.
Sorry, yeah. Okay, we'll talk. Let's talk over the weekend or something.
You bet.
Take
Have
care.
a good day, guys.
Asante, have a good day. Thank
And you. Cheers.
Take care. Bye.
Cheers.